Hello, everybody. Welcome to this session of Cloud Lunch and Learn. Today we have Shlomi Livneh with ScyllaDB, a better Apache Cassandra and AWS DynamoDB. So I will turn it over to you, Shlomi, and have a great session.
Thanks, Dwayne. My name is Shlomi. I work at ScyllaDB. I manage the development team. And ScyllaDB is a NoSQL database. We're a better Apache Cassandra and better than AWS DynamoDB. And I'll share with you in this session some facts about me. This won't be a session about how to actually develop for ScyllaDB, because you can go and read that, and there are many sources. We have those, and Apache Cassandra has a lot of sources, and so does AWS DynamoDB. If you have questions, please write in the comments, and I'll try to address them online. And let's get started. So ScyllaDB is today 120 plus people, and I manage the development team, which is spread over 15 countries. Yeah, we're really spread out. So why should you listen? Let's start with that. So we have more than 400 companies using us. You can see the logos over here. There are, of course, many more. It doesn't fit into a single slide, and there are very large companies like Disney, Kiwi, GE, Discord. Some of them are Fortune 500 companies. So hopefully you'll stay on the call. And what is unique about ScyllaDB? So ScyllaDB is unique in the sense that our solution was developed to be close to the metal and scale horizontally and vertically. What do we mean by close to the metal? So our background, a lot of the team background is in kernel development. Founders of the company is Avi Kiviti and Dor Laor. Avi Kiviti is the inventor of the KVM, kernel virtual machine, which is what drives all the clouds today. And we really understand machines. We really understand processors, latencies. And we found out when we actually tried to develop an operating system to optimize things running on top of it, that databases wouldn't scale well. And they wouldn't scale well in the sense that when we used 4-core machine and moved to 8-core, it would scale 2 times. Moving from 8 to 16, we would scale 1.75. 16 to 32, we would scale 1.5. And 32 to 64, we would actually get only 0.9. So, and the reason that the scaling didn't work is that the systems weren't designed actually close to the metal. They didn't know how to use processors well, or NUMA devices with memory spread. And neither did they know how to use SSDs that we have today. So this is close to the metal architecture. We actually designed the system so it can work and scale linearly with a number of cores. And that also touches the first point about horizontal and vertical scaling. Vertical scaling means that if you give us twice the number of cores, you'll get twice the performance at the same latency. And horizontal scaling has to do with, if you add nodes, we will scale just as well. So, and again, it will retain the ratio. So this is what we worked on, and hopefully I got you interested. So what's different about Scylla than other databases? So one, in order to get great performance, and great performance is 2 aspects for our customers, and you saw some of them. Great performance has to do with latency and scalability. To get great latency, you need to be close to the hardware. And Java and other managed languages do not really allow you that. On top of that, they have their own management threads in the background that do GC and free up memory for you. So it's simple to develop, but there is a cost associated to it. And still, you cannot go very low, close to the kernel or the hardware. C++, of course, removes all of that. You can go as slow as you want. And we even have some assembler code in our database. So that's the first item or decision we made. We're going to be close to the hardware. The second item that we followed is that everything is async, and believing things it's easier to develop some parts in synchronous manner, but it has a cost. So why is everything async? So a lot of people are used to use networking as an async device, and of course that's very easy. Disks are also asynchronous. You queue items, or the disk has queues internally. It will process requests in parallel and then return results. And it's much simpler at times to program synchronously with the disk, writing and waiting for the process to go back after the write was done, yet it has a cost. And the cost has to do with the need to add additional threads. So whenever you have a synchronous call, you actually have something blocking and waiting for the response to come back. And to cope with that, you add additional threads to your system. Threading has its own cost. So context switching between threads has a high cost. It also is not totally up to you. You have an operating system controlling it under you. And there is also a question if you're utilizing the hardware to the most or not. So Scylla is designed to work with all requests working asynchronously. And that means that we can actually have a single thread running on a core, doing networking and I/O and memory management and also processing, all in an asynchronous manner. And we don't need multiple threads. Shard per core actually connects really well to it. So on the left-hand side, you have what happens when you do threading. If you put too many threads or put too little threads or too little amount of dogs, then you'll have some resources or plates not being eaten from. And when you put too many dogs, you'll actually have them fighting over the resource and some of them waiting. And on the right-hand side, you can see when everything is perfectly aligned, which is what really happens at Scylla. You can see that you will have a single thread running, and each of it will have a CPU and disk and networking, and will be able to work as fast as it can based on your requests, actually utilizing the maximum of the hardware. And this is another diagram showing the same. So on the left-hand side, you have the traditional design that Cassandra has, where you have multiple threads. And again, the need for multiple threads has to do with the fact that you can only utilize things if you're the hardware well, if you have enough items queued up. And the operating system actually schedules things on the CPU, and the same for memory and for networking, and there is contention. And on top of it, if everybody's working on the same memory space, then you'll have cache invalidation. So on Scylla, and we're using a C-star framework that we developed below it, everything is sharded. And when I say sharded, everything, then I really mean everything. You have the memory sharded, so a single thread is only accessing that memory. That means that we can remove locks, and we do not need to use any primitives that guarantees no parallel working on them. How do we communicate? Everything is sent via queues. So if I have a different core running on this system that needs information owned by some other core, then it will send it a message. And that core will look up the memory and send back the response. In addition to that, we provide a single vCPU for every shard. And also, if possible, we provide dedicated queues, depending on the device. It will also get dedicated I/O to the disk if the disk has enough capacity. So we can reach linear scaling totally if the hardware can support it. And we really do it on the great machines that exist on the clouds today. And if we look down even lower, we can see that Scylla has its own task scheduler. And the traditional stack, you would have threads running with a function pointer and a stack which is very large or relatively large. And the context switching between the threads is large in the sense that you need to save all the stack and invalidate memory at times. And on Scylla's or C-star's execution, the execution parts are promise, future and promise. The tasks are really small, and it's very easy to queue things. Scylla uses a model where it's cooperative scheduling. So that means that tasks are relatively short. And in this model, they can also ask if anybody else wants to run. So in the cooperative scheduling manner, you have tasks actually running for short periods of time, going back, asking if anybody else wants to run, and making sure nothing hogs the CPU. In the traditional model, you have the CPU schedulers that actually serves as the adult in the room, which makes sure that if someone is hogging the CPU, then it will be context switched out and assures some fairness, but that fairness has a high cost associated with it. And usually on a single shard, we will run millions of parallel tasks. The next item that we have has to do with I/O. And going back to the discussion about how we work with devices, legacy Cassandra had a number of threads writing or reading from the disk, and the user had to pick numbers, 16, 8. How would he decide if he should set up 16 or 8 threads writing to the disk? Well, there are blogs about it, there are some guidelines, but it's not really a science. And to make sure that we actually get out of the disk the maximum capacity that we can, we developed and have been developing over the years an I/O scheduler, a user space I/O scheduler, that really looks at the hardware, at what it can do, and then optimizes for latency. So what you can see here is a case where we measure concurrency of requests being sent to the disk. And on the left-hand side, you can see how many IOPS we're doing. And you can see that at some point, the disk actually reaches a plateau. It cannot do more operations per second. And if you grow the amount of requests, or the concurrent requests you're sending to the disk will actually have to queue those up. You will not get better latencies. And the optimum is actually to select a point where you're reaching the latencies that you need and utilizing the disk for the maximum. And in this case, it's this specific point, which means that you should send around 150 requests per second, and that assures you that the latency will be less or around 1 millisecond, and this is a variance of the request. So developing this, and this is a recap, and it's much more complex than that these days. Then this is a model that we had way back in 2016. Now models are much more complex. Then you can see that we really control the flow of I/O to the disk to assure good latency of read and write, making sure that we don't send too many requests to the disk, actually assuring that we utilize the disk to the maximum while guaranteeing latency is kept. The last part that we decided to develop Scylla is that we wanted it to be autonomous. Going back to the example about Cassandra, well, there are background processes running in Cassandra and Scylla, and one of them is called compaction. Compaction has to do with Scylla and Cassandra use LSM trees. It's log structured merge trees, which means that you're writing SS tables, and there is a background process actually merging those SS tables, making sure that the number of files you need to look up for reads stays constant. It's not necessarily one, but it doesn't grow over time infinitely. And if there are overwrites, you deduct those overwrites as well. So this background operation in Cassandra is controlled by the number of threads. Again, a magic number that the user needs to figure out, and at times the user change that from 1 to 2, but there's nothing actually checking if compaction is keeping up with the write speed, and what happens when we have less writes and we have more reads, or we have more writes and less reads. What should we do? And we decided to build a system that is autonomous, meaning that no matter what the workload, if the read and write ratio changes, if the profile actually changes, then we will measure the backlog and actually change the shares the compaction can get from the CPU and disk and do the backward processing that it needs. The same happens with flushing of data from memory to disk. So there is a process called memtable to cache or memtable to disk, and those are also monitored and adjusted priority for memory management and flushing of memory to disk. So we built an autonomous system trying to cope with different workloads and different requirements coming from different workloads and ever-changing workloads. Nobody wants to tune and retune its database because they added a different workload, or retune the database for nights when you do batch processing or create reports. The database simply needs to tune itself based on the workload that it gets. So after I explained some of the technology behind us, and I hope I impressed you a bit, let's understand what really this translates to. Or in other words, why should you care? After all, I proved that we have customers, some of them Fortune 500. They bought into it because of value, not because of the slides. And what does this translate to? And those are benchmarks we released. The numbers now are much better. These benchmarks are 1 year old. And you can see that ScyllaDB versus all its competitors, NoSQL competitors, DynamoDB, Cassandra, and Bigtable, we are much better in throughput and in latency. Of course, in managed databases such as DynamoDB and Google Bigtable, the better throughput actually translates to lower costs. So, the technologies that we've been developing, and it's been developed for the last 8 years, and we keep on enhancing our capabilities, actually allowed us to get a very big benefits over the competitors. So the reason that Comcast or GE use us is because they saw those gains. And I picked up 2 different slides from 2 different customers. So this is Comcast, and Comcast actually used Cassandra. They migrated close to 1,000 nodes to 80 ScyllaDB nodes while sending 60% more traffic and getting better latencies. And overall, we saved them around $2.5 million annually. So this actually translates to savings, but more importantly, usually it translates to happy customers. The reduction of latency is actually usually a deal breaker for customers, and everybody's running to lower the latencies. And this is Disney and Hotstar. They're using us, and they are able to reach with us sub-millisecond P99 latencies and save a lot of money as well. So I promised also to talk about what's next and why customers, what's going on if we got there, what's around the corner. And we're not standing still. In the first years, we developed our technology and tried to prove that we're better, and we are better. But we are also implementing now features that our competitors don't have. And one of the items that we introduced is WebAssembly. WebAssembly is a binary format that allows execution. It was built specifically for running functions internally, and you're using it probably in your browser, even if you don't know. And what it allows you is to execute for us to execute code. So instead of pulling data out of the database and then executing code, like you do with Spark or batch processing, then you can actually send the execution to the data and do the analysis close to the data, and then get the results. And this will open up the possibility to do transformations and to do analytics close to the data, which is another space that a lot of users have to write data to two different databases. So a lot of users write their data to a columnar store and a row store because they need to process it for analytics and also process it for user requests. And we are trying to say you don't really need to do that. You can actually run analytics and online workloads, and we have the scheduler for this as well, that will guarantee low latency for your online workload and provide you to send the logic to the database to execute and be efficient. A different item that we're working on is eventual and strong consistency. Eventual consistency is common in NoSQL databases, and it provides higher throughput. Simply put it, the fact that you're using a NoSQL database means that you plan your queries and write your data at times twice or 3 times based on how you query it. And you write the data so it will be optimal to fetch it. And the way the databases, eventual NoSQL databases do that, usually they use eventual consistency because that means that you guarantee eventually that all replicas will see the data, but it's not time gap. Strong consistency is what you have in SQL and NoSQL databases, but they are much more limited in throughput. And using one database versus the other just for the fun of it is not fun. People need to learn different languages. You need to operate multiple databases. In times, you need one and a bit of the other. And we are working hard to provide both options on Scylla. So we are developing strong, consistent tables as well. And we do have today something called lightweight transactions that does allow you some guarantees, but we're working to do much more than that to provide you strong consistency. And we use it today internally to manage cluster data and user schema. So hopefully you've survived till here. I'm not seeing any questions. Maybe we'll take it in a second. So how can you get started? Hopefully you're convinced a bit that you should start. So we have university live days, and those are great to get started. We have an upcoming day on 28th of July. It's on the web. You can register to it, and I'll try to share the link in a second on the chat. And you'll get trainers working with you on a half day, trying to get you up to speed and doing some Q&A, and it should get you started. In addition to that, Scylla University has self-paced courses. You can also do that and try it out. It's really great. In addition to that, operating a database is complex. And of course, a lot of our customers like Comcast operate at their scale the database on their own. But if you really want to try it out, we have Scylla Cloud. You can create an account. We provide test clusters and free-tier clusters, and you can just log in, register, and start giving it a try. It's very, very simple. That's it. Any questions, anyone? Guess not.
Yeah, I don't see any questions in the chat.
So maybe I was too fast.
No, it was great information. I appreciate it. We'll give it a few minutes. If anybody if you're on the stream, I think that the comments for the stream, you have to be on the YouTube stream to be able to ask questions. So if anybody's on a different stream, then maybe they're not coming through. But I don't think the comments are come through on LinkedIn or Twitter, which we're streaming on all three today. We'll give it a minute. We'll give it a minute or two.
Sure.
Really appreciate the presentation here today.
Thanks for having me.
Great presentation. We'll give it a couple more minutes. See if by the bottom of the hour anybody has posted anything, and if not, we will end a little bit early today.
Okay, just so it won't be so quiet, I guess. So some items not on the slide, I guess. So I said before that we're really distributed. ScyllaDB's R&D is spread over mainly Europe, but we do have people in the Far East and Americas as well. And we're, of course, looking to hire great people. So if anybody is interested in open positions, they're all on the web, and you can find them. We are also the biggest the position that we're searching ever for is actually Go developers to work on Scylla Cloud. So it would be great if anybody's attending that is interested to apply. Aside of that, I was talking a lot about the technology, and one of the items that is key to understand is that we took the hard way. We took the hard route and the road usually not traveled in some sense, in which we didn't compromise on the core values. So we said that we wanted to build a low latency, high throughput system, and we will do whatever it takes to actually achieve that. And we didn't try to cut the corners of saying, okay, we're going to provide a configuration value that the user will set up how many writes the disk can do and how many reads the disk can do. We actually benchmark the hardware. So when you set up a Scylla node, and we do it in Scylla Cloud as well, it's the same benchmarking that you use. We actually benchmark the hardware to see what it can do. We check the hardware for networking interrupts and queues, and we optimize Scylla for whatever your hardware can do. So one of the nicest things that we got off AWS was that we're one of the few vendors that can actually use the great new devices or great machines that they put out there. And they also quote us on some of their PRs about i4i, which were just launched, and how well they are. So not compromising on core values to build a high throughput, low latency database that will actually use whatever you can give it really paid off. It's hard development, but it pays off at the end.
Thank you. Great information. Yeah, no additional comments. So I want to thank everybody who attended today. Shlomi, thank you very much for the great presentation. Hope to see you back again at Cloud Lunch and Learn soon. And
thanks, Ryan.
Yep. Thanks everybody for attending, and enjoy the rest of your day.
Bye, guys.